Hello, everybody. Welcome to my talk. I am Pratyay Mukherjee from Visa Research. I'm going to give a talk on adaptively secure threshold symmetric encryption. So the story starts with a very simple question that how to store sensitive data. If you Google that, then the first thing that pops up is encrypt your data. It's wonderful, but slightly more detail, what it exactly does is basically it reduces the storage requirement from big data to small keys. So earlier you needed to store a large amount of data, and instead now you encrypt all your data, but now you need to store the encryption key. So the next question that comes up is how to store the key. Okay, so one naive approach could be that you encrypt your data and store a ciphertext on some server and store the secret key on a separate server. Although this is a nice solution, it suffers from an obvious attack like single point of failure. For example, if an adversary breaches into the server where the secret key is stored, then it can basically decrypt all the data ever encrypted with that particular secret key. So typically in industry, what people does is basically use a hardware security module which stores the secret key, and then whenever the decryption is needed, the hardware security module can throw out the secret key and decryption is performed. Although it has a lot of benefits, there are some obvious drawbacks of these solutions. Like for example, there are a lot of side channel attacks for these kind of solutions. Secondly, there is a lack of flexibility. That means HSMs are typically bound to some particular algorithms and it's very hard to make any change to them. And then HSMs of good quality, as you can see here from the Google search, that the cost can vary from like $40 to several hundred thousand. So because of the high cost of a good quality of HSM, sometimes it's very expensive. So here we are not going to talk about hardware-based solutions. Rather, we focus on to software-based solutions. So in software-based solutions, there is solutions like provided by Vault, which basically does a secret sharing of the secret key. So it chooses different servers to store the shares of the secret key. Let's just consider the secret key split into two parts, SK1 and SK2. It's a very simple 2 out of 2 secret sharing. And then whenever decryption is performed, the secret key is gathered to one server and then it is reconstructed and the decryption is performed. So the problem with this kind of solution is that it requires reconstruction during decryption. So if you want to decrypt again and again very frequently, then it leaves the secret key on memory for a long time. And due to this exposition, it sort of suffers from this kind of attack is called snapshot attacks, where the adversary can breach onto the server on this particular moment, take a snapshot, and can acquire the secret key. So that becomes a big security issue. So basically, we are looking for solutions where we want only software-only solutions, but without any reconstruction of the secret key. So the first thing that comes into a cryptographer's mind is use techniques like general multi-party computations, where you can think about the server storing the secret key like SK1, SK2, the shares, and then they interact to compute this following function that's decrypt on this XOR of this SK1 and SK2, and then output the decrypted value. There is a line of work that actually does this kind of approach, where mostly they do MPC of the AES. So one particular good point of this solution is that it can compute any scheme. For example, AES, which is a standard encryption schemes, and then it can comply to standard. But there are several other drawbacks of this solution. For example, it's not a scalable solution because it's either highly interactive, that efficient MPC algorithms takes basically much more than 2 rounds. There are optimal MPC solutions that takes exactly 2 rounds, but often they are very inefficient. They rely on tools like fully homomorphic encryption or something similar. Also, they are kind of bandwidth intensive because typically all the servers need to talk to each other. So the overall communication cost become order of n square. And furthermore, MPC solutions typically works with Boolean circuits. So if you want to use MPC for like say AES decryption, first you need to convert AES to a Boolean circuit, equivalent Boolean circuit, and that will lead to a lot of blow up in the computations. So overall, although there are certain benefits like complying to standards and like flexibility of using any scheme, it suffers from severe efficiency issues. So in 2018, a paper called Distributed Symmetric Encryption or DISE, it's my work along with Agrawal, Mohasel, and Rindal. And we proposed this solution that basically formally defined this problem of distributed or threshold symmetric encryption. So in this paper, we defined threshold symmetric encryption via intuitive game-based definitions, and we achieve security like privacy and authenticity. So it basically works like a distributed version of authenticated encryption, and it works up to T-1 malicious corruption. We proposed a generic construction in that paper, and that's based on any distributed pseudorandom function in some sort of black box manner. And our solution only required 2 rounds of communication, which is basically round optimal. The responders don't interact. That means the communication is basically order of n. And there are several implementations that was done in the paper. It's instantiated with 2 different DPRF constructions. So both of them actually are basically first proposed by Naur, Pincus, and Reingold in 1999. One of them is based on public key operations and reduces to DDH assumptions, and another is like just from PRF-based solution but has some sort of limitation. However, one drawback of this solution is that in that paper only consider static corruptions, whereas this work we actually consider adaptive threshold symmetric encryption. So what we did is we augmented the security definition from DISE, like formally defined adaptive threshold symmetric encryption, and we have again like privacy and authenticity both for malicious but adaptive corruptions. Our construction is actually exactly same as DISE. So we do not propose any new construction, but we showed that if DISE construction can be instantiated with any adaptively secure DPRF in a black box manner, that actually achieves our definition. So we formally proved that in this paper. So we instantiated with a augmented version of DDH-based DPRF using this idea from this work by Libe, Joe, and Jung. Their work actually worked for adaptive threshold signature. We incorporated ideas from that paper and augmented the NPR's DDH-based DPRF to an adaptive setting. So additionally, for a stronger definition, we also require adaptive non-interactive zero knowledge. And for that, we propose a simple construction random oracle model. Furthermore, we showed that the PRF-based DPRF construction that was also used in DISE is actually kind of optimally secure in the adaptive setting. So in this talk, we will be focusing mostly on these particular adaptive DPRF-based constructions, and we'll briefly talk about why the PRF-based DPRF is also optimal. So in the rest of the talk, first, I'll be briefly describing the intuitions of adaptive versus static security. And then I'll be talking about NPR's DDH-based DPRF construction and why their proof actually do not work with adaptive corruption. Then I'll be talking about our DDH-based DPRF construction that uses ideas from LJY. I'll give proof intuitions. And finally, I'll briefly talk about why NPR's PRF-based DPRF constructions is actually optimal in the adaptive setting. Okay, so let's talk about adaptive and static security. So what happens in static security is that there are parties And parties are basically uh, corrupt like at the very beginning of the security game or the execution. So once the parties are corrupt, then the protocol starts executing by rounds after rounds and so on. Whereas the adaptive setting, as its name suggests, parties gets corrupt at sort of any point of time, and it becomes strictly stronger than static security because at this point the corrupt party can take part in some interactions. It gathers some information from this round one interaction, and based on that it can decide to corrupt either of the two parties that's depicted here. For example, based on this interaction, it decides to corrupt this party, and then it can again take part on the further interaction. It can basically dynamically corrupt any number of parties as long as the total number of corruption stays within the limit. So in this case, we consider a threshold t, so the total number of corruptions will stay below t at all time. So, slightly more formally, in the proof of static security, the simulator gets to know the set of corrupt parties in the beginning, but in the adaptive security, that doesn't happen. So, that's why it's kind of challenging to prove anything in the adaptive corruption setting. Okay, so now let me talk about NPR's DDH-based DPRF construction. So the construction is as simple as that, taking a hash of the input and raising it to the power of the key k. And when you're in distributed setting, then the k is basically secret shared. So here let's consider a very simple example where 3 out of 3 setting. So k is basically additive secret sharing of k1, k2, and k3. So party 1 will have k1, party 2 has k2, and party 3 has k3. So on input X, each party will do a partial evaluation, which is basically very similar to the final evaluation. Instead of like raising to the power of the whole key, they raise to the power of their part of the key. So in particular, party 1 does hx to the k1, party 2 does hx to the k2, party 3 does hx to the k3, and so on. And then on receiving the partial evaluations, y1, y2, and y3, they can be combined simply just by multiplicating in this case, and that will lead to the output of the DPRF as the exponent will be added. So now in the proof, the goal is to show that DPRF X is pseudorandom as long as DDH holds, but the difference from the standard PRF setting or the non-interactive setting is that this should hold even if the some number of parties are corrupt. So let's consider this reduction, which has the DDH tuple G to the A, G to the B, and G to the C. So what happens in the proof is that it implicitly sets the value A, let's say A, to the key K, right? So it's implicit. That means that it does not exactly know the value A or K, right? But it implicitly somehow uses that. So now the adversary corrupts parties like party 1 and party 2 in this case. And once the reduction knows the corrupt set, and that's why using the fact that this is a static corruption, so then the rest of the sort of simulation is kind of simple. It can just choose random k1 and k2, and that still leaves the entire k undefined because it does not know k3, right? So it can know k1 and k2 and give them back to the corrupt parties, and then can use the k3 as sort of the unknown factor and can simulate the entire game. So that's the basically overall idea of that pseudo-randomness proof of this DPRF construction. Now it's not too hard to see why this fails in the adaptive case, because this is very crucial that it knows the corrupt set, right? So what happens in the adaptive case is that the corrupt set is unknown. So let's try to see what happens if it executes the exactly same steps. So let's say the adaptive corruption happens for the party 1 first. So it chooses random k1, k2, and define again k3 is equal to a minus k1 minus k2. This is like implicit definition. However, now the adaptive party decides to corrupt party 3 instead of party 2, right? So the reduction can give k1 to the party, but now the reduction does not know k3. So then that becomes a problem. It cannot really simulate this corruption, right? So that's why basically the proof fails. And in fact, slightly more detail, what exactly happens is that it's choosing these, k1 and k2 randomly. So it's basically it's guessing the corrupt set ahead of time, and in this case that turned out to be wrong, right? So now, if you are in the case of t out of n, and then if every time reduction needs to guess the corrupt set, then that's bad, right? Because then the possible number of corrupt set is like in the order of n choose t, and if t is like, somewhere in the middle, so of course if t is constant, this n choose t is like not a big number, but if t is somewhere in the middle, like over 2, then n choose t becomes like exponential. So the reduction will only be successful with negligible probability. So that's why the proof does not work for adaptive case. So let's see how we can fix it. So we take the idea from LJY, adaptive threshold signature. So what we do is, instead of having exactly one key, now we have sort of two parts to the key, like parts U and V, and we use two basically random oracles, hx to the u and g to the g of x to the v, and the rest of the schemes is basically exactly the same. So u and v are secret share. So this should not be like XOR, that's a typo, sorry about that, and it should be like a plus. And then everybody computes their evaluations, like partial evaluations, and the combinations is exactly the same, right? So now let me briefly talk about the main idea of the proof. So the main idea is that reduction always knows entire key U and V, and hence it can actually give correct key shares for adaptive corruptions. It's kind of simple to imagine that if the reduction always has the key, right? So earlier we saw the reduction does not know the entire key because it sort of uses the DDH exponent as its key. So in this case, if the reduction can know the entire key, then it becomes basically trivial to simulate. But we have to make sure that that becomes consistent with the other information the adversary gets. And for that, we use random oracle programming in such a way that adversary does not have enough information about K from the other parts. So basically K has enough entropy, and that sort of we leverage in the proof. Okay, so let me briefly talk about the hybrids that we use in the proof. So the real game is kind of simple, and we just show that how the real game simulates the random oracle queries, because then in the next hybrid we'll change that. So random oracle query on any x or any xi is simulated as hxi equal to g to the ri, and gxi is equal to g to the si for random ri and si. That's kind of a standard simulation technique. You choose a random exponent and raise to the power of the generator. However, in the first hybrid, we do it slightly differently, that we choose a W, which is random, and instead of choosing Ri and Si randomly, now we program Hxi is equal to G to the Ri and Gxi is equal to G to the Wri. And note that this W stays the same for all Xi queries. So for Xj, it will be G to the Rj and G to the Wrj, right? So the W becomes common in these two cases. And it's not too hard to see that these two experiments are basically computationally indistinguishable as long as DDH holds, because we basically making this change in the exponent, and you can simulate this via just plugging in that actual DDH value. And since we're not changing anything like the actual keys and everything, so this is like completely independent of the keys K, right? So then the entire rest of the experiment can be simulated perfectly. The reduction knows the key K, so everything goes smoothly. So what happens in the next hybrid is we'll be changing how the eval queries are responded. So in hybrid 1, the eval queries are responded correctly. For example, eval x is responded with hx to the uj. This is for party j. That's why the index j times gx to the vj. So in hybrid 2, this is quite different, that eval x is responded with g to the zj, where zj is basically a random value, right? So z is basically a random key and zj is its share, and it's responded with this particular value. And now why this is okay to do, because note that what happens in the eval case here is uh, eval of x is become hx to the uj times gx to the vj. So according to the simulation, it becomes like g to the this quantity, like ri times uj plus w times vj, right? So now this is like a universal hash functions, as long as u and v are basically randomly chosen, and they are the key of the hash functions. R and w are the inputs, right? And since it's like a universal hash functions and it's statistically close to a random value z, it's okay to instead just sample a key zj and just exponentiate to the generator. And that's why these two experiments are statistically indistinguishable. So now, interesting to see that eval queries are actually completely independent of the actual key k, right? So now at this point, the reduction can always know the key k and simulate the eval queries independently. And whenever a corruption query from the adaptive corruption comes up, it can send the corresponding key to that party. That's how the simulation is possible. Now, this is a very high level overview of this proof technique, but this actually really simplifies the entire proof. So compared to the DISE DPRF proof that as done in the CCS 18 paper, this proof is much simpler because of this particular adaptivity feature. So now let me briefly talk about the PRF-based DPRF construction and why it's optimal even in the adaptive setting. So here let's consider 2 out of 3 threshold, because otherwise it's a little bit hard to explain. So in the 2 out of 3 case, the DPRF is basically PRF of K1 and PRF of K2 and PRF of K3 and XOR of all of them, right? And the key K is consists of different PRF keys like K1, K2, and K3. And parties are distributed the keys such a way that any two party will have all the keys. So in this case, it's kind of simple that first party will have the first two keys and second party will have K2 and K3 and last party will have K3 and K1. Like the partial evaluation is kind of simple. It evaluates the PRF on the inputs on K1 and on input K2 and so on. On receiving all these values, it basically chooses the correct value, and that's the output of DPRF. So now if there are like t out of n parties, if t is the threshold and it's somewhere in the middle, the efficiency scales with n choose t. So now, since the efficiency already scales with n choose t, now we saw that the reduction can always guess the now corrupt set with a loss of 1 over n choose t. So that basically adds a one more constant factor, and that's why it's basically already adaptively secure by this simple guessing technique. So finally, summarizing that, we have defined and constructed adaptive threshold symmetric encryption in this paper. We instantiated with a new adaptive DPRF, and it suffered from about 2x slowdown compared to DISE, which is a pretty good trade-off to get a much better like adaptive security. The adaptive DPRF proof is conceptually much simpler than the static one, and it's particularly more prominent for the malicious corruption. So you also provide a stronger adaptive DSE we did not have time to talk about, but that requires a adaptive zero-knowledge proof, non-interactive zero-knowledge proof for a specific commit and proof statement in the random oracle model. As a future work, we can think about removing random oracle without compromising efficiency for this particular TSE scheme. With that, I conclude my talk. Thanks a lot for paying attention.